Okay, so we are now going to start the exercises of the next chapter, that is the 14th one. And this is the first one. Here we have to verify that the set defined in example 3 is an ideal. So we have to go back to example 3. In example 3, the ring that is there is any commutative ring R with unity. Okay, it can be any commutative ring with unity, and there is an element A in R, which is also any arbitrary element in R, and the set that we are talking about here is this subset of R. That is, it is the set of the elements in R that are multiples of A by ring elements. We have to prove that this is an ideal of R. So let's see how it can be done. First of all, the set has to be non-empty, which is clear because R is a non-empty set. So this is also a non-empty set. But anyway, let's just mention that. Okay, in the solution, note that because we have the reference here to example 3, so we do not have to write these things again in the example. We already know what example 3 is and what we are talking about here. Note that this is a non-empty subset of the ring R. Now, to verify that this is an ideal, we have to check two things. If we take any two elements from this subset, then their difference should belong to this subset, and then that other thing, that product of an element from this set and an arbitrary ring element. Actually, two products are there. That is, you take any element from here, say K, and any element, say B, in the ring, then both the products BK and KB should belong to this subset. Okay, so if all these conditions are satisfied, then this will be an ideal. So let us first verify that this is a subgroup of R under addition. So let's take two elements from here. Let R1A and R2A belong to this, where it is understood that R1 and R2 are some ring elements from R. Then, by elementary properties of any ring, R1A minus R2A is equal to R1 minus R2 times A. By elementary properties I am saying because this involves not just the right distributive law, but some other things also, which involves, for example, here actually I am using this fact that if you are considering any two elements X and Y in a ring, then these identities are true. So that fact has also been used in getting this thing. Now this is again an element in R of this form, so it belongs to the subset in question. Also, for any ring element R in R, R times R1A is equal to R1A times R, because we are dealing with a commutative ring, so the order of the products don't matter. And this is equal, okay, perhaps I should have written this first, but anyway, by associativity of multiplication in the ring, this can be written as R1A, but then again this is an element of that form, so this belongs to the subset. So this is an ideal of R. So that is the solution. It's pretty simple and straightforward. Next, to verify. Okay, so the first few exercises are just verifying some things that we have in the examples in this section. Verify that the set A in example 4 is an ideal, and that there is something else also, that this A is actually this. So for this, let's recall what the ring is here, and then let us also recall what the set A is. The ring here is the ring of polynomials with real coefficients. That means our familiar Rx. That is this ring. This is the ring here. The ring of all real polynomials. And the set A here is the set of those polynomials in Rx whose constant terms are 0. Okay, so that's what the set A is. Now we have to verify that A is an ideal. Obviously A is non-empty, and let's not mention that, okay, it's understood. So we straight away go to the conditions for an ideal. So let us consider two real polynomials in A, and additionally, after showing that A is an ideal, we have to show that it's actually this, which has a name also, no? It's called the principal, I mean this thing is called the principal ideal generated by that element X. Then f of x looks like this, since its constant term has to be 0, so it will look like this. If you want, you can write one more term, a n minus 1 times x to the power n minus 1. I am not doing that, okay, it's understood that this number n will decrease as you write more terms, plus, let me at least write a2 x square plus a1 x, and a0 is 0. Okay, that is the constant term which is 0. And similarly, g is also one polynomial of that form. Say bm. This n and m may not be the same, so I am using another letter. b1x. Okay. Now, what do we have to see? We have to see that the difference of these two polynomials is again a polynomial whose constant term is 0. And the difference, I mean, you can of course see that that is the case, but still, let's write systematically then f of x minus g of x will be equal to what? Okay, now you see, because n and m can be different, so in order to write something in place of this difference, actually write what the polynomial is going to be, it's better to make these two things equal. Of course, if n and m are different, how can you make them equal? But what you can do is that depending on which one is greater than the other, you can replace one of these polynomials with an equivalent polynomial, okay, in which that number n will be the same as the other one. These remarks may sound very vague. Let me just show it, what I am trying to say here. If you want, you can just simply write, we can clearly see that since f and g have both their constant terms equal to 0, so clearly the constant term of f minus g is also 0. But you cannot do that all the time, right? Sometimes you have to see for yourself at least why that is 0. Assume without loss of generality that say n is greater than or equal to m. Then what we are going to do, n is greater than or equal to m. So we will make g like f. Okay, we are going to change g in such a way that it would look like f in this sense. Then g of x is cn x to the power n and so on plus c2x square plus c1x, where now we need to say what the ci's are, where ci is defined like this. When your I lies between 1 and m, then your ci is just bi, right? Because that's what g is here. If your I lies between 1 and m, then ci is defined to be just bi. If I lies between 1 and m, and if there are higher values of I, for those values ci is just 0. So you can clearly see that this g of x, this one is nothing but that one in fact. If your I is this. Now, now you can calculate the difference quickly, because now you have in here and in there as well. So f of x minus g of x will be this. So the f coefficients are what they are, the ai's, and the new g coefficients are the ci's. So it is just a, yeah, something happens here in this part, I don't know what. Just give me a moment, okay? In that part, when I start writing, the ink dries almost instantly. Okay, so where was I? F of x minus g of x. The f coefficients are ai and the new g coefficients are ci, and we have n. So an minus cn a2 minus c2 x square plus a1 minus c1 x, and clearly you can see that here also the constant term is absent, that means it's 0. So that's why it belongs to that set A. Next, let h of x be any real polynomial, okay? Then the constant term of h of x times f of x, which is also the same as f of x times h of x, is 0. But why? That question remains. Now we have put so much effort in showing that the difference has its constant term 0. So we should also equally show that this product also has its constant term 0. But this part I leave to you. Okay, you have to use the product formula, and from that formula you have to figure out why the constant term is 0. Keep in mind that the constant term of f is 0. We already have that. But the constant term of h may not be 0 because h is an arbitrary polynomial coming from our ring. Still, the product will have its constant term equal to 0. And let me at least remind you what the product looks like. The product is just going to be this, no? F times h of x would be summation. Okay, I don't want to again write, because I would have to write the expression for h of x, and you know what this thing is going to be. It involves, it's a polynomial after all, but where each coefficient is given by a sign. You know what that is. And anyway, we are not really interested in calculating the whole product, but only the constant term. Okay, so that you will see how that is 0. So h of x times f of, actually it's very easy to know what the constant term here will be. You don't even need the entire formula. but I won't say anything more on this. Thus, A is an ideal of our ring. And now we have to show that the ideal A is actually the principal ideal generated by the polynomial x, the monomial x. And that is rather easy because we have already chosen arbitrary elements f and g in our ideal A. Now we can say that A is an ideal, and you just concentrate on the element f. Note that what was f? F was this, no? A n x to the power n. Let me just write the next term also. Plus a2 x square plus a1 x, and you can clearly see that you can take x common out, so to speak, and write this thing as this product a n minus 1 times x to the power n minus 2 a2 x plus a1 times x, where of course this other polynomial is again coming from our ring. So that means any element in A is a multiple of the monomial x, and that's what tells us that the ideal A is just simply the principal ideal generated by x. Hence, this. Next, 3. Verify that the set I in example 5 is an ideal and that if J is any ideal containing any ideal of R, okay, that contains these elements, which of course are there in the definition of I itself. These elements are there. Then I is a subset of J. Hence, this ideal, which actually is nothing but I, okay, it's the notation that denotes I. It's essentially an extension of that principal ideal concept. in a principal ideal, all the elements are multiples of a single ring element. Here, in place of a single ring element, we have a number of elements, finitely many elements, and the elements here in this subset are not multiples of these elements, but it has some other structure. Okay, sum of multiples of these elements is the smallest ideal of R that contains these elements. Alright, so the first job we have at hand is to recall what we have in that example. So the thing that we have in that example is again a general ring R, a commutative ring R. R is commutative and it has a unity. Okay, there is an element 1 which acts as an identity element under multiplication, and what the example does is it considers finitely many elements in R and then defines a subset of R like this, I, which also is denoted by this symbol. It's purely a symbol, a notation just, okay, and the definition of that itself is just this. Rn where these Ri's are coming from our ring R. So that's how the elements in this set look. Okay, so the elements have this structure. In words, each element in this set is a sum of ring multiples of these elements, A1, A2 and so on up to An. Now we have to prove that this I is an ideal. Non-emptiness of I is obvious, so we are not going to repeat that here either. So we start by considering two elements in I. Let A and B belong to I. Then A is equal to say R1 A1 plus R2 A2 and so on plus Rn An, and B similarly is another such element, say S1 A1 plus S2 A2 and so on plus Sn An. For some Ri and Si coming from our original ring R. Okay. Then what about A minus B? We need to first of all show that A minus B is also going to be an element of that form so that it can belong to I. using the ring properties, elementary properties in a ring, you can see that this will be r1 minus s1 times a1 sorry, plus r2 minus s2 times a2, and like that, plus rn minus sn times an. And since these differences are after all ring elements, that is elements in R, so this clearly belongs to I. Also, for any R belonging to R, we have AR equal to RA, because we are in a commutative ring. And now you put the expression for A. The first step is to apply the left distributive law, well, its extended version, to have this R times R2 A2 plus R times Rn An. And the next step is to use the fact that multiplication is associative in a ring. So using that, this expression finally becomes R times R1 R1 times A1 plus R2 times A2 plus Rn times An. And then again, this has that same form that the elements in I have. So this belongs to I. Hence, I is an ideal of R. Okay, but now we also have something else to show. We have to additionally show that if J is any ideal of R that contains all these elements A1, all the AIs, then I should be contained in J. In other words, I is the smallest ideal of R containing these AIs, these elements. So let's do it in the next paragraph. Let J be any ideal containing these elements. Okay, so that means these are elements in J. Now, using the fact that J is an ideal, you will have this. Then for any ring elements Ri, R1 A1 plus R2 A2 and so on plus Rn An must belong to J. Why? Actually, it happens in two steps. Because say you concentrate on A1, okay. A1 is coming from J and R1 is a ring element. Since J is an ideal, so R1 A1 will be an element in J. That's how all the Ri AIs are elements in J. But again, because J is an ideal and hence a subgroup of R under addition, the sum of these products also belongs to J. But this is an arbitrary element in I. So this implies that I must be contained in J. Okay, so now we have the solution. Next, four. Find a subring of this ring. The direct sum of two copies of the ring of integers, that is not an ideal. Not an ideal of this. Now you may come up with your own subring in this ring, which is not an ideal, but there is one particularly easy one which is known already. Consider the subset A consisting of those ordered pairs of integers where the coordinates are the same. So to speak, the diagonal, actually as a set, this is a Cartesian product, right? Of that Cartesian product, this is the diagonal. Now let us show that this is a subring. Clearly A is non-empty, of course, that's the first thing. Let us take two elements in A. Then the difference of these two ordered pairs in our ring is just the ordered pair where the coordinates are the differences of those coordinates by the definition of the binary operation in the original ring. That is, this is equal to this ordered pair. And of course, since x and y are integers, so is x minus y. So that's why this belongs to A. Also, what happens when we calculate their product? In that case, again, by the definition of multiplication, it's just the product of the corresponding coordinates. So again, this belongs to A. Hence, A is a subring of our ring. But A is not an ideal. To show that it's not an ideal, see, being a subring, A is a subgroup of the ring under addition. So that already has been established. So the other condition must fail. Note that this element 1 comma 1 belongs to A, and you can consider this element from our original ring, say 1 comma 0. But what about their product? The product is 1 comma 0 because component wise multiplication, and this of course does not belong to A because the coordinates are not same, and that's why, since this product fails to be in A, so A cannot be an ideal. So A is not an ideal of our ring. So this example shows that we may be tempted to conclude something like this, that maybe all subrings are actually ideals, but that's not the case. Here you see a subring that is not an ideal. And let us see one more. The fifth one, let S be the set of all complex numbers A plus Bi, where A and B are integers and B is even. So that means actually these are Gaussian integers, right? Complex numbers whose real and imaginary parts are integers. But even among all the Gaussian integers, we are considering those in which the imaginary part is an even integer, and such Gaussian integers form the set S. Show that, just like this one, show that S is a subring of the ring of Gaussian integers, but not an ideal of it. So the approach is same. You consider two elements. S of course is non-empty, one can see that. For example, an element in S would be 1 plus 2i. Okay, so that would be an element in S. So S is non-empty. So we straight away consider two elements in S. Belong to S, so that A1, B1, A2, B2, these are all integers, and where B1 and B2 are even. Then plus B2i is equal to A1 minus A2 plus I times B1 minus B2. And note that since B1 and B2 are both even, their difference is also an even integer, so that's why this complex number again belongs to S. And also what happens to their product? A1 plus B1i times A2 plus B2i. So the product will be A1 A2 minus B1 B2 plus I times A1 B2 plus a to b1. Now note that this integer may not be even, because the even parts appear only here, and that does not matter also, because it just needs to be an integer, which it is. But here, due to the evenness of both b1 and b2, a to b1 is even, and so is a1 b2, and that's why their sum is also an even integer. So this product also belongs to S. Hence, S is a subring of the ring of Gaussian integers. But now you have to show that it's not an ideal. Okay, and for that, what is it that you have to show? You take an element in S and you take an arbitrary Gaussian integer and show that their product is in fact not an element in S. And that part actually I am leaving to you to come up with such complex numbers so that this would happen. You consider something, some concrete complex number, okay, say 1 plus 2y in S, and then I'm not saying that this would work, you also take some such concrete complex number I in the ring of Gaussian integers, so that their product is a complex number whose imaginary part, of course it will be an integer, but it's an odd integer, so that the product will not belong to S. So this part I am leaving to you. You can write in the comment section below what you come up with, or if you are unable to come up with anything, then also let me know. I will do it in the next video, but provided you write some comment. Okay, otherwise I will just move on. And that's just it for tonight. So in the next ring update on Gallian, we are going to see the other subsequent exercises and their solutions. And tomorrow, of course, we have our analysis upload. So see you tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.